Hi everyone, my name is Chris Elrod, and I am happy to talk to everyone today about loop analysis in Julia, in particular LoopVectorization.jl, which is a library that it focuses on representing loop nests, and with the primary aim so far of optimizing them to make them run more quickly. So today I'll be discussing the basics of sort of like what intra-core parallelism is, to give you an idea of sort of what is going on in the CPU and how large speed gains can be had, versus a very naive thing. With the note that, of course, Julian LLVM automatically does a lot to take advantage of this. So with that in mind, I will then be moving on to a few examples that will demonstrate or help you consider like when you can actually expect to see a large gain in performance with using loop vectorization. And then finally, I'll discuss a little bit more about how loop vectorization represents loops, and then demonstrate some other exciting things that we can potentially use it for. With the note before sort of moving on, that loop vectorization currently does have some limitations in that it assumes that each iteration of the loops can be performed in whichever order that it wants, that there's no definition to this order currently. And because of that, that provides, of course, gives it all the freedom it would want to take advantage of any parallelism that it desires or that it deems is profitable, which is currently only intra-core parallelism. Sort of inter-core, like using multiple cores, is something that's sort of left to the user as a higher level optimization that has overhead, and is there for something that you should probably is left to you to manage and decide what the best way to do this is for your programs. So now, starting with sort of what two main components of intra-core parallelism here. The first is SPMD instructions, which is single instructions or single instruction multiple data, which is a single instruction can operate on multiple elements of a vector at a time. So, modern CPUs, most of them have vector registers with 128, 256, or 512 bits being particularly common. What this means is that a 512-bit vector, for example, can hold 8 float 64 or 16 float 32. So a single instruction operating on these vectors will, for example, an add instruction will then be adding 8 float 64s or 16 float 32s. So you're doing a tremendous amount of work per instruction. And for the most part, there's very little overhead in terms of number of clock cycles that it takes to actually complete, and how many, so like throughput in terms of instruction per clock cycle. There it tends to be negligible or no overhead for these SPMD instructions, with exceptions existing for more complex instructions like square roots or divisions. Now, something that is important to hold in mind when you are writing your own code is sort of the layout of your data in memory and how you access it. So I will go over this in a very heuristic manner, and to say that sort of if you wanted to create a vector, sort of represented here in this bracket, of x5 through x8, loading from, this is a vector in a CPU register, loaded from a vector in memory of x1 through x20 or so, that loading contiguous elements like 5 through 8 is very fast. And similarly, if you had this vector register and wanted to store it into your memory into memory, and you wanted to sort contiguously, that is again very fast. Similarly, even if it wasn't a multiple of 4, or a multiple of 2, one of these power of 2 sizes, that is you could mask off parts of the vector using masked instructions or applying an off-mask register depending on the instruction set, and again, this is very fast. Similarly, broadcasting a single number across a register is also fast, but for example, if you reducing a vector into a scalar, however, is not and takes multiple instructions to accomplish. Much slower, however, is if you did not have contiguous blocks of memory that you were loading or storing from the registers. If gathers and scatters, gather being if you had different places in memory that you wanted to load into a single register, and a scatter where you had a register that you wanted to scatter across. These are much slower, and therefore ideally you can arrange your memory layout to choose a memory layout for your program such that the operations you want to be performing in parallel involve contiguous loads and reads. Now, the other major component of intra-core parallelism is superscalar parallelism, which is that multiple instructions can be executed at a time, and that many can be in flight at a time. So on one hand, we had the SPMD, which is that each instruction is working on multiple elements of data. We also have parallelism from there being multiple instructions. The key takeaway here is that because sometimes there are dependency chains, such as if you're trying to calculate A plus B plus C, you would need to wait for A plus B to have finished computing before you can start calculating that sum plus C. Therefore, if your computation was just one long dependency chain, you would have to wait for each instruction to complete before being able to compute the next instruction. And because it's often the case, like for an add instruction, that recent CPUs are capable of executing sort of 2 with a throughput of 2 per clock cycle, but it takes 4 cycles for any particular one to complete. That basically you, instead of achieving the 2 per cycle, if you had a dependency chain, you would be limited to 1 every 4 cycles. So as an optimization, you would have to sometimes unroll a loop to, rather than accumulating into a singular number, you have multiple accumulations. That way you are still able to, this is so that way you're able to take advantage of this superscalar parallelism. So making sort of an example that hopefully you can sort of visualize, or by just seeing this code and seeing how we change it to take account of there's the SPMD optimization where we replace this scalar sum where we have a dependency chain where we're adding to this one number every time in the loop to now adding 4 numbers at a time within this loop. We sort of unroll this loop for this vector width of 4, and then we're adding 4 at a time as for the SPMD optimization. Then the next optimization here for superscalar parallelism is that we'd said, hypothetically, that we have potentially 2 additions per clock cycle, and it takes 4 clock cycles to complete. So on each iteration of this for loop now we have, clock cycle 1 starts adding these 2, clock cycle 2 begins adding 3 and 4, then 5 and 6, clock cycle 4 adds 7 and 8, and then clock cycle 5, these 2 additions are done, and we can begin the next 2. So now with this, we're able to achieve the 2 additions per clock cycle, and each addition is also adding 4 numbers. So that ideally this would be a rather fast summation algorithm. or summation implementation. Of course, not actually written like this, like you wouldn't be slicing arrays like this, but just sort of representing the actual operations that are being performed here. And then at the end, we have to sum up all our accumulation vectors into one vector, and now finally we can turn this vector into a scalar. So this is also something that for the most part LLVM does, and Julia does by default very well. Something that is missing from this example, of course, is that tragically, by some cosmic oversight, not all vectors happen to have lengths that are a multiple of 32 or 64. I don't know why not, but it just seems to be that that's the case. So we have to handle the remainder. And now what LLVM does for the remainder is it adds one of these scalar loops to just finish off the remaining 0 to 31 elements. However, unfortunately, it's the case that this is actually much slower than, many times slower, because then we don't have any of this parallelism at all, than this vectorized portion is. So even if a vector is very long, it is easy for the remainder to take longer to sum up than than it is the vectorized portion. And we can see that here with by running benchmarks, where I adapted the sum example to being a squared norm. So instead of sums, we have FMAs. And now here I'm benchmarking this vector of length 799, 768, and 800. And we can see that it takes roughly twice as long to do 799 elements, over twice as long as it does to do 768 or 800. So this remaining 31 on top of 768 takes longer than it does to do the 768, which is, of course, less than ideal. Now this, as a note, this problem is exacerbated in AVX 512, like this computer that I'm running on has, because now we have, a longer remainder longer unvectorized remainder. So with AVX2, it will be, on average, half the remainder. Therefore, the problem is half as bad. But this is still not an ideal scenario. Now, one of the optimizations that LoopVectorization does is that it also vectorizes the remainder of the loop. So that way, when we do 799 elements, instead of being over twice as slow as 800, it's more or less, it's barely slower at all, and roughly in line with the performance of 768 or 800 elements. So now, when you have loops that are likely to be dominated by this remainder calculation, which is going to be more severe the shorter your loops are, then that would be likely a place where using loop vectorization and add AVX is going to be profitable. Another case where it's profitable is special functions like log, because the base Julia log implementations are not, or log, sine, cosine, exp are not vectorized, while loop vectorization uses a different implementation that is SIMD, and therefore it's able to calculate this log determinant of a triangular matrix much more quickly than, for example, the implementation in the standard library linear algebra. We can look at another example here that I don't want to go into too much detail, just showing workarounds of some of the limitations, and also note sort of a memory layout of StructArrays as a library that maybe you should look into at your own time, but is something that can sort of work around the fact that imaginary and real numbers tend to be interleaved, which as we said, is sort of not what we want because we're doing SIMD across loop iterations. So structive arrays now suddenly makes all of the imaginary, all the real numbers contiguous, and then loop vectorization gives us a SIMD syncos, so that now we can calculate cosine imaginary sine much more quickly than the base implementation. So now, another area or another optimization that loop vectorization provides where we can get a substantial performance benefit is in that it tries to eliminate any redundant loads that it can. Well, any redundant operations, but the most extreme examples, the redundant operations are loads. So what I mean here is if we look at this sort of matrix multiplication example, we have here in the inner loop where this FMA operation of A times B plus C depends on all three loops, but loading from A does not depend on N, and loading from B does not depend on N. And similarly, we don't need to sort of store, well, I guess we already wrote that we are only storing C when we're done. But, so, you think of the basic idea here is that we want to sort of reload these as infrequently as possible. So by unrolling both the M and the N loops, we get to reuse for every time we unrolled N, and we get to reuse this B load for every time we unroll N. So by unrolling both of these loops, we have a lot of reuses of this data, and if we call, let's say, U1 and U2 the times that we unroll the M and N loops, then we have sort of U1 plus U2 total loads versus U1 times U2 FMAs that we're capable of doing. So that sort of really mitigates this sort of memory problems and load-bound nature of sort of how this loop was actually written, and lets us actually begin to saturate the two potential FMAs that we're capable of doing and achieve a lot of gigaflops that way. Now, this is here I just made a very small size problem just to show how, I guess, easily we can gain much better performance over the static arrays implementation by just defining a couple overloads. Here, check args is to allow M arrays to actually use loop vectorization. By default, arrays that are not dense would opt out. And then we also want to be able to, loop vectorization to be able to learn the actual dimensions of an M array. So we can define these to do so. And for good measure, I also create regular base Julia arrays that I evaluate this on to show that even the base arrays are, for 7x7 arrays, that this is much faster than the static arrays or the M arrays. And loop vectorization, given static size information, is, again, over twice as fast as it was without. So, it's very easy to make sort of these optimized small matrix operations in this manner. A little more interesting for most people is probably that the flexibility of if we come up with sort of arbitrary tensor multiplication like things, that we're also able to apply it there. So here I show einsum, which just creates a bunch of loops and adds at SIMD. Teleo, which uses loop vectorization if you loaded loop vectorization as a just convenient means, because I think most of us really like this index notation. And then finally, in case you want to see what the actual loops look like written out with loop vectorization, and we can benchmark here and see that we have 100 microseconds versus 3 milliseconds. So we have a 30-fold speed gain by using loop vectorization here for a somewhat larger problem. And one of the great things about loop vectorization is that it works by creating a generated function and then using this to try to infer type information from related to memory layouts, such as reading permuted dimmers arrays to find out which memory loads are actually contiguous. And because of that, it will be able to actually reorder the loops as necessary in order to get good performance, even when even as, or from the same function, even as the underlying data layout is changing. Now, another example of this sort of load saving that is probably best shown by sort of routing things out a little bit, and comes up a lot in convolutions, and that is if you have a sort of a memory access that is being indexed, or with a sum or minus of two of the loops, that if you then unrolled both the M and N loops threefold, as in this example, you end up with a lot of redundancies. So instead of, or by unrolling both of them, instead of having 9 total loads, 4 of them are redundant, and we're left with only 5 loads. So this, again, is able to give us a nice savings. And returning to this example, where I sort of just defined a convolution with @avx, as well as sort of just a baseline inbounds fast math version for comparison, as well as nnlib for a much better optimized than this as a comparison. We now have benchmarks for a sort of smallish sized example here. I chose 28 by 28. So, okay, here. A little more background here is convolutions are commonly done for image processing, and for neural networks. So we wanted to evaluate here like a batch of 50 28 by 28 images, which was the size of MNIST, but I added 3 colors just to make things a little more interesting, and we see that we are close to 4 times faster for this size than nnlib, and 30 times faster than the base version. And this it extends or continues for larger sizes. So just very quickly on sort of more that can be done is, to start with just how loop vectorization represents loops internally, is that it doesn't actually save the sort of representation how you wrote it. What it records is the dependency relationships between the operations expressed in it, as well as between these operations and the loops. So what this conveniently allows us to do is that means that we can then sort of just apply the chain rule to these to get sort of the adjoints of the loops. So here in this matrix multiplication example, where we had loading from A, loading from B, and then FMAing with this accumulator before finally storing in C, we are then able to get the partial derivative with respect to this loop and A and B, and then we have this set of operations that involves FMAing. Long story short, is that we end up, FMAing like C bar, which is sort of the adjoint, the gradient with respect to C, which was the output of this loop, and a load from B, as well as C bar and this load from A. which then are being sort of accumulated here as implied by this difference in loop dependencies. And essentially what this equates to is that this gives us the two more matrix multiplications, which are actually the adjoints of the original matrix multiplication, and hence this loop nest object gives us the adjoint.